This is lecture 22. Today we'll be talking about mixtures of gases. We'll actually be hitting on several topics related to gases. We're actually going to start by jumping back to the ideal gas law for a minute and just talk about how we can find the molar mass and the density, or how those are related to our ideal gas equation. So if you'll remember, the ideal gas law or ideal gas equation is PV equals nRT. And our molar mass, right, that's equal to the number of grams per mole of our species that we're talking about. And grams or mass is generally, we generally use an M to express that, and moles is expressed with an N. You'll notice there's an N in the molar mass term, and there's also an N in our ideal gas equation. So if we solve both of these for N, we can combine the two equations. And then if we do that, we can then rearrange the equation to solve for molar mass. And what we find is that the molar mass is equal to the mass of our gas times RT divided by pressure and volume. So if we're able to measure the mass of a gas, then we can actually use that information to find its molecular weight, which can be very useful. If you can get a pure gas into a cylinder, then measure how much the mass of that cylinder increased when you filled it with that gas, then you can determine the molecular weight of your gas without using any fancy equipment. So this was a very early way of figuring out how much different masses weighs by using this, or different gases weigh by using this equation. The ideal gas law can also be related to the density of our gas, or we can use it to figure out our density. So in this case, you'll notice that density, that's equal to mass divided by volume. And there is a volume term in our ideal gas equation. So again, we can combine these. If we combine them and solve for density, we get this equation. So density equals mass times pressure divided by the number of moles times RT. So to figure out this, you're going to have to know the mass of the gas and the number of moles. You'll notice that that ratio is equal to the molecular weight here. So your density is actually just going to be equal to your pressure times your molecular weight over RT. And so this is how then you would calculate your density of, say, a mole of an ideal gas. And the takeaway with this equation is essentially just that as your molecular weight increases, your density is also going to increase, which makes sense because your density is just mass per unit volume. If your mass is increasing, your volume staying the same, then of course your density is increasing. Well, let's give you a practice problem with the ideas we just talked about. I'm going to ask you if you have 1 mole each of argon, carbon monoxide, bromine 2, and F2 at standard temperature and pressure, which of the following lists them in order of increasing density here? So I actually don't have the masses of all of these memorized, but I do know roughly where they are on the periodic table. For example, I know that carbon and oxygen are lowest on the periodic table. Since they are both lowest, those two added together are going to be our lightest gas. The next element on the periodic table is fluorine, so F2 is going to be lighter than Br2. And I actually know, I can remember that argon is in between fluorine and bromine. Argon actually weighs 40. And if you'll remember, the density of our gas is just related to its molecular weight. So if we're listing these in order of increasing density, I'm just going to start with my lightest species, which is carbon monoxide. Hey, look, that shows up first in option B. Then comes my next lightest gas of F2. Then comes argon and Br2. So B is going to be our correct answer here. And I'll show you something cool as a result of this high density of bromine here.
Bromine vapor is roughly 5 times more dense than air. It can be poured from one flask to another. The density of bromine, like that of all gases, is proportional to the molecular mass of its molecules in the gas phase.
So bromine, since it's so heavy, can actually settle down out of air. And if there wasn't turbulence in our atmosphere, like wind and weather, then we could actually get a stratification of the different gases in our atmosphere as well, right? Air is made out of nitrogen gas, oxygen gas, argon, water vapor, CO2, etc. All these gases actually usually weigh between about 18 grams per mole and about 60 grams per mole, if I remember correctly. So they're all kind of in a narrow range. We don't have any big, heavy gases in our atmosphere. CO2 is one of the heaviest gases in our atmosphere. Just because heavier gases, since they get so dense, they'll actually settle down at the bottom or out of the atmosphere, which is pretty interesting, I think. All right, so that covers our molecular mass and density. So far in dealing with the ideal gas law, we've just been talking about one gas at a time. But as we've also said over and over again, most gases, like the atmosphere, are mixtures of gases, right? If you smell the smell of food that you're cooking in the kitchen, or your friend or spouse or parent or somebody's cooking in the kitchen, that smell is also adding other gases to the atmosphere, usually not just a single one. So how do we deal with the pressures and volumes and so forth when we have more than one gas? To figure this out, we're going to turn to John Dalton, man in profile. All right, so John Dalton came up with a law of partial pressures. They're pretty quick and loose with the word law back in the 16 and 1700s. So they just came up with law after law. Now we've just combined them all into simpler laws or more comprehensive laws. But he said that for a mixture of ideal gases in a container, the total pressure is equal to the pressure of each individual gas. To put that more explicitly, he's saying that the sum of the pressures, or the total pressure in a container, is the sum of the pressures each gas would have if they were alone. So if we think of oxygen being in a tank by itself and nitrogen being in a tank by itself, they're going to have some pressures. If we mix those two pressures together, then the new total pressure is just going to be equal to the pressure of the oxygen and the nitrogen. And so we refer to each gas as having a partial pressure. Partial because they are making up a part of the total pressure. And it's just adding, which makes it really nice, right? When we have these simple equations. So then the total pressure depends on the total number of molecules present, not necessarily on their identities, at least for ideal gases. And often we'll use this law for simple routine calculations, even for non-ideal gases. It's still a fairly good law that you can just add these partial pressures together. So what does this look like in practice? Well, let's say that you're a scuba diver, and you're a scuba diver with a tank on your back, and that tank has 20 atmospheres of pressure from O2, 40 atmospheres of pressure from N2, and 140 atmospheres of pressure from helium. And that's all in your scuba tank. What's the total pressure in that tank then? Well, the total pressure is just going to be equal to all of those pressures added up. By the way, we put plus ... here to indicate that if there's other gases with pressures, we just keep adding them, right? So this isn't limited just to 3 gases. It could be just 2 gases. It could be 5 gases. It could be 27 gases. Right, so we're just going to add up the pressures of these. We get 20 atmospheres of pressure from oxygen, 40 from nitrogen, and 140 from helium. So our total pressure in the tank is going to be 200 atmospheres. All right, let's relate this partial pressure idea then back to the ideal gas law. So it turns out that each of these, P1, P2, P3, can be written as its own ideal gas law, where P1 is equal to N1 times RT over V. Now here's an interesting question for you. Why don't we put a 1 on the T or the V here? Well, we don't put a 1 because if we are in a mixture, all of the gases are going to be in the same container. So the volume is actually going to be the same for gas 1 as it will for gas 2 and gas 3, right? Each of these gases will spread to fill its container. Okay, so we'll get this mixture of gases. The temperature as well is going to be the same for all these gases. Even if we put gas 1 in while it's hot, gas 2 in while it's cold, they're going to mix and equilibrate to the same temperature, if we give them a sec. So if each of these has its own ideal gas equation, we can actually substitute this ideal gas equation in for the different pressures. And we'd get this: the pressure total is equal to N1 RT over V plus N2 RT over V plus N3 RT over V, et cetera, et cetera. And if you know anything about algebra, which I don't know if you do, hopefully you know something, but you can actually factor out all these moles because all these RT over V values are the same. So we can pull all the moles out and say that our total pressure is equal to the number of moles of gas 1 plus the number of moles of gas 2 plus the number of moles of gas 3 times RT over V. So we only have to plug this part into our calculator a single time. We can also say, if we sum up all those moles, that our total pressure is equal to the total number of moles times RT over V. So both these last two equations are consistent with the problem we had in the last lecture, where I asked you about a balloon with 8 moles of hydrogen gas and 4 moles of oxygen. And when we calculated that out, we just added the moles of the two gases together, just like we're doing here. All right, so there's a unit that you'll often see used in these kinds of questions and in other kinds of questions, and that unit is the mole fraction. I guess this isn't really a unit so much as a ratio, but what the mole fraction is saying how much of the gas is made up of gas 1, how much is gas 2, etc. So each gas, though, has its own mole fraction. And the mole fraction of a given gas is just defined as this. It's usually denoted with an X. Actually, that's a lie too. This X is actually the Greek letter chi, but you can just think of it as an X. So the mole fraction X1 of gas 1 is just equal to the number of moles of gas 1 divided by the total number of moles. So then, of course, the second mole fraction, and the mole fraction for species 2, would just be N2 over N total. All right, let's say then we have a mixture of 16 grams of oxygen, 14 grams of nitrogen, and 4 grams of helium gas in a 22.4 liter tank at 273 Kelvin. What is the mole fraction then of oxygen? So you'll notice in this mole fraction equation, these are moles, not mass, right? So we need to convert all of these into moles, figure out how many moles there are of each. So oxygen gas here weighs 32 grams per mole, so 16 grams will be half a mole. 14 grams of nitrogen. Nitrogen gas is N2, which weighs 28, so 14 grams will be another half mole. And helium, of course, is a monatomic species. It's just one atom, and it weighs 4 grams per mole, so 4 grams would, of course, be 1 mole. We then need to add all these moles together. In this case, the total number of moles will be 2 moles. We're looking for the mole fraction of oxygen, so we'll just take this 0.5 divided by 2, and we'll find that the mole fraction is 0.25. So put another way, this is how we figure out this is how we express or calculate what percentage of our total gas is the gas of interest that we're talking about here. So we would say that this is 25% oxygen. Let's let you practice with this idea. If the total barometric pressure in the room you're in, let's say that you are sitting in a lecture hall in Provo, Utah, and that the pressure in the room is 0.95 atmospheres because we're a little bit above sea level, what is the partial pressure of argon? So for this question, I'll tell you that the partial pressure is equal to the mole fraction times the total pressure. So this is an equation that we can derive just from the equations on the last two slides. You're also going to need to know that air is made up of all these different gases. So it's 78% nitrogen, 21% oxygen, 0.9% argon, and has trace amounts of CO2 and water. Go ahead and pause the video right now. See if you can figure this one out. All right. Now, one thing you have to understand to get this is something I could have explained before telling you to pause it, but you need to understand that this percent is the percent in terms of moles. So 0.9% of the moles of gas are argon, which means that this 0.9% is just equal to our mole fraction up here times 100%. So to solve for the partial pressure of argon, we're just going to take the total pressure of the system times the mole fraction of argon. The mole fraction of argon then is just going to be this 0.9% divided by 100%, which will get us 0.009. And then the total atmosphere is 0.95 atmospheres. We'll multiply that together, and we'll find that the answer is 0.0086 atmospheres. Okay, now let's put this into a practical perspective. We will look at a real-world experiment that used to be extremely common. It's not as common anymore, but one thing that was fairly common is when chemists wanted to figure out how much gas was released by a reaction or other process, what they would do is they would carry out the reaction in a closed system, and then as gas is produced, they had this line hooked up that would run through water up into an upside down beaker. The beaker would be full of water. So ideally, there wouldn't be any gas at the top when you start this experiment. But then what they would do is as the experiment goes on, the gas comes through and bubbles up through the water, gets collected up here at the top. So as it's filling with gas, right, the space in here, there's going to get that bubble and it's going to be expanding. And it's going to keep expanding so that as you add gas, the total pressure inside here is equal to the atmospheric pressure outside, right? So what we're doing is just pushing down on this water. We're pushing down on it until we're pushing down as hard as the atmosphere is also pushing down on the outside. Right? So this is actually a great way for chemists to see how much gas is coming off of a reaction. There is a little bit of a catch though, is that while you're doing this, this beaker is not only filling with your reaction gas, but water also vaporizes and always just has some amount of what we call vapor pressure or some amount of partial pressure in the air. And so it is going to have some partial pressure contributing to the total pressure in here as well. So we're going to have to subtract off that partial pressure. And that partial pressure you'll often see listed as a vapor pressure. So vapor pressure of a liquid is always just the partial pressure of that liquid that you'd get in a closed container. So it's the maximum amount of pressure of that liquid that can be turned into a gas. So let's look at an experiment like this. So let's say that we have this sample of KClO3, that formula is right here. If you heat this enough, it'll actually react to where this oxygen gets released in the form of O2 gas. And if we bubble this in then through this apparatus, the gas is going to pass through our water and come up in here. So let's say we're doing this at a water temperature of 25 degrees Celsius. So the temperature of the water really controls the temperature of the gas because the gas is coming in through the water. So not only is the tubing being cooled by the water or heated by the water, but the gas is also in direct contact with the water and gets cooled down. Okay, and the total volume of the collected gas is 329 mils. So we make a bubble in here that's 329 mils, and it has a pressure of 0.979 atmospheres, which would of course just be the pressure of the atmosphere outside of this. So you don't have, the reason I say that is because you don't have to put any special apparatus in here or anything to measure the pressure inside. It's always just going to be the same as your outside pressure. So the question though is how many moles of oxygen are formed in this reaction? Okay, we know that enough oxygen came in to displace 329 mils of water at a given pressure. First thing we have to figure out in this question though is what gases are even being collected. So we know oxygen is coming off, but we also know that the water is vaporizing to some extent, and we have vaporous water or gaseous water in this bubble as well. So the gases being collected are O2 and H2O gas, which means that the total pressure in here is equal to the pressure of the oxygen plus the pressure of our water. So what we need to do then is solve for the pressure of our oxygen. So we'll subtract off the pressure of our water, which is just listed as a vapor pressure up here. So at 25 degrees Celsius, water has a vapor pressure of 0.0313 atmospheres. And so the the partial pressure of oxygen is going to be 0.9477 atmospheres. Then of course it asks how many moles of oxygen are formed. So now that we know the pressure here, we know the temperature, and we know our volume, we can just use the ideal gas equation, solve for the number of moles, and plug in numbers. Of course, you'll notice we converted from degrees Celsius here to Kelvin. Other than that, everything just goes in as is. Oh, sorry, we also had to convert from milliliters to liters here. If you use milliliters, you'll get a much bigger number. And we find that we made 0.0127 moles of oxygen gas. Okay, so that is partial pressures. That is the ideal gas law with molecular weight and density. Now let's go back to our kinetic molecular theory. So we started our conversation right about gases with this kinetic molecular theory. We made several assumptions about the volume of the molecules compared to the container, their motion, their collisions, whether they're interacting with one another or not, and their average kinetic energy. So all of these assumptions are true for ideal gases. But gases aren't always ideal. In fact, most of the time they're not. And even assumptions like this top one, where we say that the volume of our gas is insignificant compared to the container volume, even this one breaks down in certain cases. So this breaks down if you have a small volume or if you have high pressures. So for example, you can have a volume that can only accommodate a few atoms or molecules at a time. A great example of this is carbon nanotubes. So carbon nanotubes are literally just made out of really big rings of carbon that then are stretched out in a tube of carbon. And all these carbons are connected to one another. And so this is small enough that certain gases can flow through easily, whereas other gases can't flow through this carbon nanotube because they get clogged trying to go into this tube. And then this other assumption, number 4, that these molecules have no intermolecular interactions, this is actually almost always false. So it turns out when all these ideas were being figured out, they were using low pressure gases at high temperatures. But at low temperatures, pretty much everything interacts with each other. Even noble gases like helium still will interact to some small extent with other gas molecules. We'll get into why that is in a later lecture, but today we're going to finish off by talking about how to correct for these volume and interaction effects on our ideal gas equation. We're going to do that using what's called the van der Waals equation. So if you look at it, the van der Waals equation is actually fairly similar to the ideal gas law. So we still have pressure, we still have volume, and we have our nRT over here. So you're basically still doing pressure times volume equals nRT, but now we're correcting for the pressure, we're correcting for the volume, right? So we have our measured pressure here, and then we have this big old correction factor. Now in this correction factor, you'll notice that we've got n squared. So this correction factor is going to depend on the number of moles squared. And then we also have the volume squared. So the bigger this gets, the lower these interactions are going to affect you. And then we have this A term. This A term is a constant for each gas that describes the attractive force. Now, you might think that A stands for attraction or so forth, but what it actually stands for was the first letter that van der Waals thought of. Right, now over here, we still have our volume of our container, but we're also going to now start correcting for the volume of our particles. So in this case, you have the number of moles times a number essentially related to the size of a mole of the gas molecules. What you'll notice, van der Waals used the letter B here. So the first one he thought of was A, the second he thought of was B, which I think we're all fine with. All right, so all this stuff over here is what we call the corrected pressure. So we correct the pressure for these other factors. And then this stuff over here is what we call the corrected volume. So sometimes you'll see the corrected pressure and volume written as a P apostrophe or V apostrophe. And then this equation basically looks exactly like the ideal gas law, right? P apostrophe times V apostrophe equals nRT. And this equation is actually much more useful than the ideal gas law. It's much more useful because it gets you correct answers much more often. All right. And then these two constants, A and B, those are just different constants for different gases. So each gas has its own constants. So for example, for O2, O2 has an A value of 1.36, but water has an A value of 5.46. Now, you'll notice that water's value is much bigger than oxygen's. So what is the big difference here? Well, we'll actually spend a bit more time on this later, but the big difference is H2O has two polar bonds, right? Oxygen is much more electronegative than hydrogen, and so it's going to have two dipoles. So H2O is going to be a polar molecule, whereas O2, both oxygens have the same electronegativity, so they're not going to be interacting as much. So the dipoles in water causes this correction term for the pressure to be really high, which means that in here, your pressure gets a big bump from those intermolecular interactions. All right, let's look at how this corrected van der Waals equation compares to the ideal gas law. We'll do that with chlorine gas. So chlorine gas has an A value of 6.49 atmospheres times liters squared per moles squared. So it's got to have those liters squared and moles, negative moles squared, so that all the units in this place right here cancel out except for atmospheres. So we're adding pressure in atmospheres plus atmospheres. And then similarly, the B term is in terms of liter mole or liters per mole, so that when we multiply it by the number of moles here, the moles will cancel out and it'll be just volume in liters minus liters here. Okay, but those are the A and B terms for chlorine gas. Let's calculate the pressure of 8 moles of chlorine gas in a 40-liter tank and at 27 degrees Celsius, and we can figure out if it's behaving ideally or not. So if it was behaving ideally, we would calculate its pressure using the ideal gas equation, right? And that would give us a pressure of 49.3 atmospheres, just based on the number of moles, the volume, and the temperature here. And if this is not behaving ideally, we need to consider the van der Waals equation. And since we're looking for pressure here, we'd have to solve this big nasty equation for pressure. And so we just get a different big nasty equation here. So then we would plug in our number of moles in 1, 2, 3 different places. We'd plug our volume in a couple places. We'd use our A and our B term, and then our R and our T. So we plug all that in, and we'd get a pressure of 29.5 atmospheres, right? Which means that chlorine gas is very non-ideal. Its pressure is decreased by a whole 20 atmospheres because of the volume that's taken up by the molecule and by the intermolecular interactions. And you'll almost always notice that the intermolecular interactions is a much bigger number than the volume, because the intermolecular interactions are really what's going to be driving this the most. Well, let's give you a practice problem, see how you're doing with this idea. Which of the following gases is most likely to behave as an ideal gas at high pressures or low temperatures? So I have 4 gases here: helium, CO2, CH4, and N2, and I have their A and B terms listed here. So go ahead and try and think through this, and go ahead and pause the video and then we can go over it. Right, the correct answer is actually helium. Why is it helium? Well, if I write out my van der Waals equation, then I get this pressure plus N2 or N squared A over V squared times V minus NB. And you'll notice that helium has really small A and B terms. They're both almost 0. And if A is actually 0, then this whole term, so A times N squared over B squared, is going to be 0. So we'll actually not be adding anything to our pressure term. Similarly, if our B term is close to 0, and you'll notice all of these none of them are very different. B terms are usually pretty consistent unless you get into the really big molecules. But nonetheless, if the B is about 0, then this term also goes to 0. In which case, if those both go to 0, we just go back to the ideal gas law. So in other words, low A and B values mean ideal behavior. All right, we'll give you one last problem here. I want you to tell me, what is the pressure of O2 at 20 degrees Celsius in a typical portable compressed tank? So this portable compressed tank usually has a volume of about 2.24 liters with 15 moles of O2 in it. These are used by patients suffering from chronic lung disease. So either you're smokers or people that are born with a congenital lung defect, etc. I have van der Waals equation right there for you. Go ahead and pause the video and try and solve this one. All right, all we're doing is plugging in numbers, right? Now, this is a big equation, so if you don't get the answer right, it's probably because you typed it into your calculator wrong. You're going to have to use parentheses, etc., or type these parts in kind of one at a time and write them down, etc. Also, make sure you're converting from degrees Celsius to Kelvin. But beyond that, we're really just going to be plugging all these numbers here in. These numbers are still on my slides, so if you want to practice with this problem until you figure out how to enter everything right into a calculator, go ahead. But we're going to end up with a volume or a pressure of 143 atmospheres. So this tank is pretty pressurized, right? You don't want to damage it in any way, or you can cause serious harm. All right, let me know if you have any questions about any of that.